Welcome back. Here we are again looking at PB's Math64 extension library, whatever you want to call this thing. Side project, whatever. This is a Math64 64-bit exclusive Math64 library. So all the operations it performs are in 64-bit. We don't have any integers, there's no bytes, no nothing like that, no floats, no 32-bit floats at all. Up until now, we've had a bunch of, we can do basic operations, add things, subtract, etc. I've got some operators in there as well. We can do comparisons between them. We can do some Boolean type logic stuff. But we didn't have any way of making, jumping around in the logic. So the script started and it fell through the code in a linear fashion. So here's the old test here. It's in this highlighted out as a string in there. So it would fall through the instruction by instruction by instruction. Now, to do things like if statements or loop statements, or which is all we probably really need, we need to have a way of branching around inside the code. And for that, we need a few different things. So we need to phrase, in this case, I've just used if statements, the same as what same way as what PB works. So we've got an if. This is an example of if else and if. I'm not going to support an if then statement. I probably could, but there's issues with if then statements that are kind of irritating sometimes. When people stack things on lines and they expect the if then else to work, and then the phrases gets lost sometimes. And I probably should look at the logic of doing that again. But I can't be bothered for this extension. It's not really worth it. You can nest the statements as well, as shown in this part here. So let's run this example in 165. On the left we have the PB window, on the right we have the debugger. All the information is being displayed to the console in the debugger. So over here, saying the compile status was okay. So we've got a source code, which is a bunch of declarations. We're doing a comparison with D, which should be 0 by default when the script starts. We're going, is D less than 1,000? Yes, it will be. So this logic falls through, and then we execute the E equals 1. We hit else, we branch out of here over the if statement. Do the next thing, is D greater than 1,000? Nope. We fall down through the second trace here. Below is our variable stack inside the script engine, the compiler pretty much. I've done some of these things a bit different than the way they're implemented in PB. I'm always looking for what I feel is the best solution for something. It's amazing sometimes that small changes can make big differences to how this thing performs. Anyway, let's have a look at the bytecode here at the bottom. We've got a comparison operation, comparing variable or stack offset 3 with this absolute. Is it lower than this thing? Okay, cool. There's another stack offset there as well. So literals in comparisons become effectively variables. They're a preceded variable actually. So the status of this is held in variable 11, which is this temp register down here. To hold the status, we're doing a compare and then a branch on 0, whatever that register was at the time, and we're jumping over. Now, one difference to PP, how PB's runtime works, even in pretty much all the different revisions of it, is that this uses relative branching. So if I copied the bytecode here and moved it to a different part of memory, these branches would still be accurate. In PB they wouldn't be. You'd have to run back through and alter the branches, make them relative to where they are in memory. So run the thing, nothing special happens. We get our output is E and F are set the way they should be set. Performance-wise, in this particular bit of code, we're doing 450 million instructions. Now that's misleading because not every instruction in the script is being executed. So don't take that as verbatim. So here, even though we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 instructions, not every instruction is being executed. So some of these moves are being skipped because the logic is branching around over them. The cool thing is that's up and running. I had a bit of a problem initially with actually in the Fraser itself. This is the actual library itself. This is our jump instruction, so it's a relative jump. So we're grabbing the current address of where we are in memory. We're recasting it to this particular structure. The C-compiler will work out this is the same address and just use the same address as opcode, but it's kind of a clumsy C way of doing it. So we can use the jump and do an offset from this location here. This is where in the bytecode we're jumping to from this point. And I think that's probably a better way of doing jumps in general, because it means you don't need to have what's called a relock table, which is like a way that we can reposition, or once a bit of code is loaded into memory, we run through and make modifications to the code for what address the code is loaded into memory. But long story short, we now have a way of doing comparisons. We can select pathways for the script to run. And the idea for that really is to try and get to a point where our script could do something more than just do a calculation. It could do some logic and make decisions inside the script instead of us having to call a script, get a result, make some comparison about what's occurring, and then call a second script or a third script to take care of that pathway, if you understand what I mean. Pretty crazy stuff. So I think at some point we can probably get it to run or come close to doing these kind of dot particle stuff, as to see if we can get it to run a real world example. Because really, at this point, it's kind of a hypothetical thing. It works. It does what it says in the box. It's not pretty. It's not laid out in any way. I doubt it will ever be pretty in the way people would want these things to be. But it's there. It's an extension that's there. It's free. You can use it. You have to work within the constraints of what it can do, and hopefully it can give you a bit of a performance boost for things that are very heavy on floating point math, or in situations where you need to do 64-bit operations because you want to call a library that has 64-bit parameters. If you're thinking, oh well, how can I call those libraries? Well, when you call a DLL in 32-bit applications, it splits the 64-bit data into two chunks of 32-bit. That's how it's done. And PB is 32-bit if you didn't know that already. I guess one day we'll go 64-bit, but not for the time being. If we did, this kind of library would be superfluous. Although really having these kind of specialized, very narrow-minded libraries that to do this one particular job is really a better way of doing many things, not just a floating point. If you think about it for a second, if you have, I've talked about this a while ago, I guess, but like pixel processing kind of stuff. If you had a language that does, well, if you're writing a bit of code that needs to alter an image or something like that, then running it through PB's runtime, your code, you can probably find ways of tuning up what you're doing and getting it to a point where it's pretty optimal. In some situations, though, you would get to a point where you would need very specific, laid out, simplified instructions that can activate or use some of the internal processor architecture to benefit what you're doing. Because most of the time we can't. We're solving problems in a linear fashion, and the way to harness modern processors is to use parallel processing in general, and we can't do that. But if you had like I'm just talking out of, off the cuff really, but if you had like a point, if you're reading a point from somewhere, or a little script where you could go, almost like a shader. I talked about this a long time ago, this idea of PBSM. And the reason why that's a useful thing to have is that, again, it simplifies the instruction set. The only things it does are the least number of instructions that you possibly have, which means that the runtime to execute that logic is smaller, it executes faster than any PB code you can ever write. So you might have the same logic, but mapped over into here. And that's why this is why our 64-bit library here is probably going to be faster than doing the same thing in internal floating point operations, because to solve that, to do that, to execute that code at runtime, we're running through PBs, much larger, much more complicated. Well, actually, it's not much more complicated at all, really. It's the same level of complexity, but the more generalized something gets, the less efficient it is at solving very specialized problems. And doing purely floating point stuff is a specialized problem. This same principle can be extended to use, not just 64-bit registers, but you can have like a vector library that did the same thing. So you lay your code out in such a way where you've got the data set up in a way that you can feed to your vector library. It does the number crunching processing for you. When it's finished, it spits back a result. And life goes on as normal. And that would work out better, not just effectively in runtime land. That would work better in real life sort of, if you're translating something into machine code. This math library here, since it's very specifically designed to do one thing and one thing only, it would be very simple to convert this code into assembly and run it back into a DLL. Much simpler than doing something like PB to DLL does, because that has to take the entire language, look at the context of everything, and try and generate logic that's efficient in all the general cases. There are situations where it probably doesn't make the best decisions about how it should implement something. Anyway, didn't want to have a whole blather on session, but here we are with our little math library thing, and I'll put this together, put the next upload up, and might try and do the particle thing with it, and if I've got time. Got a few things to do, but if I've got time to do it, then I'll have a go. I can see some optimizations in this bytecode. Some things that kind of bother me, and that's one of those annoying things. If I have more instructions, I can solve some problems better, but the more instructions you have, you end up with caching problems as these things get bigger. Select case statements or jump tables in general, the smaller the set, the smaller the runtime, the better the performance. That's, again, look, it's general advice, but that's pretty much what my observation of it. And for me, I'm more interested in things performing pretty well on older computers, so we can keep that, you know, reasonable performance all the way through. I mean, it's easy to take advantage of some new feature that just cuts off old systems completely, but then it's not very friendly, really. You know, if we want to do that, we should just go, well, okay, we'll set a point in time where we just go, no, we're not going to support anything beyond this date, which is what most of these projects end up doing. Anyway, getting sidetracked again. Thanks for watching. We'll put this up on the forum, and you can play with it yourself. Stay cool. See you later. Bye.